In our final video, we're going to talk about doing calculus with logarithms and exponentials. We're going to start with derivatives. So we're going to fix a number b, which is positive and not equal to 1. So if we start from the definition, the derivative of our function b to the x is the limit as h goes to 0 of b to the x plus h minus b to the x over h. If we remember that b to the x plus h can be expressed as b to the x times b to the h, we can factor a b to the x out of the numerator. Because x does not depend on h and h does not depend on x, we can actually pull this b to the x through the limit, provided that our function is differentiable at 0. So we're just going to assume that we can do this for right now. So if we take a look at the piece in the parentheses, this is the limit as h goes to 0 of b to the h minus 1 over h. We're going to rephrase that. We're going to think about h as being 0 plus h, and we're going to think about 1 as being b to the 0. So we're going to rewrite this. And what we can see here is, if we take a quick look at this, this is actually the derivative of our function f evaluated at 0. So we can see that if our exponential function is differentiable at 0, then we know exactly how to compute the derivative of our exponential function. You take the derivative at 0 and you multiply it by the exponential function. So to sort of sidestep the problem of actually computing a derivative, we're going to make a definition. So we're going to define the number e. E is for Euler in this case. Leonhard Euler was a famous mathematician in the 19th century. So we're going to define e to be the number such that the derivative of the function e to the x at 0 is equal to 1. So we've sort of cheated here, and we've said to ourselves, oh, we're just going to define one exponential e to the x that has tangent line with slope 1 at the origin. Asking ourselves, well, why is that helpful? Using the formula that we had before, this tells us exactly how to compute the derivative of e to the x. So in some sense, we've sort of rigged the game here by defining this particular base, the natural exponential e, to be the one whose derivative is itself. Right? The derivative of e to the x is e to the x. This is nice. It also tells us something about antiderivatives. In fact, knowing that the derivative of e to the x is itself says that up to a constant, the antiderivative for e to the x is, well, itself. So now that we know how to compute the derivative for this exponential function, we can use the logarithm with base e, which we call the natural logarithm, to compute the derivatives for all other bases. Once we have the natural logarithm, we can actually change between bases by simply remembering that for any number b, which is larger than 0 and not equal to 1, we can express b as e raised to the natural log of b. If we raise both sides of this equation to the x power, then we get, so here we have in the exponent of the natural exponent e, x multiplied by the natural log of b. That is the same thing as b to the x. So if we want to compute the derivative of an exponential with an arbitrary base, we can simply compute the derivative of the right-hand side using the chain rule. We remember that ln of b is simply a number. So x times ln of b is actually a line with slope ln of b. That is, the derivative of x ln b is simply ln b. So now we know how to compute the derivative for all exponential functions, no matter the base. Some are easier than others, but they're all basically the same, up to a constant. So we need one more piece of information so that we can get at the logarithms and their derivatives. So our theorem says that if we have a differentiable function, f, with an inverse, and we have this seemingly strange condition, the derivative of f evaluated at f inverse of a is not equal to 0, then we can conclude that f inverse is also differentiable at a. Moreover, we can explicitly compute the derivative. So you can see, once we've computed this derivative, why it's important that the derivative of f evaluated at f inverse of a is non-zero. Namely, the derivative of the inverse at a is 1 divided by this non-zero quantity. So the natural question to ask is, how is this helpful? Well, this tells us exactly how to compute the derivative of the natural logarithm. So as a corollary to this theorem, the natural logarithm is differentiable on 0 to infinity. So the reason for this is, let's take f of x to be e to the x. We know the derivative of e to the x, that's simply e to the x. So when x is strictly larger than 0, we know that ln of x is well defined. So that tells us that we can compute f prime of f inverse of x for positive values of x. Moreover, we know that they're non-zero. This tells us that we can apply the theorem, and simply the derivative of the natural log of x is 1 over x. By a similar trick to what we did to compute the derivatives for the arbitrary exponential functions, we can do change of base from log base b to the natural log to compute the derivatives of the other logarithms. Since the natural log of a number is again just a number, we can move the 1 over ln of b through the derivative, compute that the derivative of the natural log is 1 over x, and then we see that the derivative of log base b of x is simply 1 over ln b times x. So now that we know the derivatives, let's check into some antiderivatives. So before we write down an antiderivative, we're going to compute the derivative of the natural log composed with the absolute value function. So we observe we have exactly two cases. Either x is positive or x is negative. In the first case, when x is positive, we know the absolute value of x is just x itself. So we get that the derivative of the natural log of the absolute value of x is 1 over x whenever x is positive. The interesting case is when x is negative. When x is negative, the absolute value of the negative is negative x. So when we take the derivative, we can use the chain rule. The derivative of ln of negative x is simply 1 over negative x, multiplied by the derivative of negative x. These two negatives cancel each other out, and so we're left with 1 over x. So this is an interesting observation. Even though the derivative of the natural log of x is 1 over x, the natural log itself is not the full antiderivative for 1 over x. To get the full antiderivative, we have to throw in the absolute value bars. So there we have it. So this last piece of information actually gives us something really handy. We currently know antiderivatives for a few trig functions. We do not yet have antiderivatives for either tangent or cotangent, secant or cosecant. So we'll do tangent first. So we write tangent as sine over cosine, and we make the substitution u equals cosine of x. However, if you were to look this up in a table of integrals, it is unlikely that you would see it in this form. Usually, one pulls the negative 1 inside the logarithm as a power. Cotangent works similarly. Your substitution will be sine theta, or sine x, instead of cosine of x. Secant is much trickier. You can do this with a u substitution. However, the u substitution is highly not obvious. So we make a rather strange observation. That observation is if I take secant of x and I multiply it by secant x plus tan x, I'll get secant squared plus secant x tan x. One can recognize that secant squared is the derivative of tangent, while secant x tan x is the derivative of secant. So with this rather bizarre observation in hand, one can make the substitution u is equal to secant x plus tan x by multiplying and dividing secant x by secant x plus tan x. So if you let u be secant x tan x, then you'll notice distributing across the top, we'll get du. So we can see that we match these two highlighted sections up. The highlighted section becomes our du. So we can see that the antiderivative for secant of x is the natural log of the absolute value of secant x plus tan x plus c. Cosecant works very similarly, except instead of using secant x plus tan x, you're going to use cosecant x plus cotangent x. The trick is exactly the same. That is all the information that we need. Everything else is just using all of the rules that we've learned in this new context.